right. In this video, we're going to talk about looking at a change of variables or a substitution formula for double integrals. So let's go back and do a review from Cal 2. And if we remember, we were able to take a function of x and use something, I think your book called it the substitution formula. And convert it over to a function of u times a conversion factor times du. We didn't actually call it that back then, but that's what we were doing. Let's look at an example of what I mean by that. Let's go ahead and use the substitution formula to evaluate the integral of x times the square root of 1 minus x with respect to x. So back when we did this, first step was we let u be equal to the same thing we always do, that is the bigger piece of the piece that's being raised to a power, which in this case is 1 minus x. Then I believe we took that equation and we solved it for x. So if I move that x over here to the left and then move that u over to the right, I should get that x is equal to 1 minus u. We then took this formula, or either one of them actually, I'm going to take the x formula, and we went ahead and took the derivative of x with respect to u, and the derivative of this side with respect to u is just -1. Then multiplying both sides by du, we get that dx is equal to a -1 du. We then took those three things and we plugged them back into our original integral, and we were able then to do what's called a change of variables or substitution formula. And what we found in this case would be that the integral of x times the square root of 1 minus x with respect to x would be equal to the integral of, well, everywhere we see the quantity 1 minus x, we're going to put in a u. For single x's, we'll put in 1 minus u, and for dx, we'll put in -1 du. So first I have an x, which is going to be 1 minus u. Then I have a square root of 1 minus x, which would be u to the 1/2. And then I have a dx, which is a -1 du. And if we look at what this gives us then is we took an integral which had a function of x with respect to x, and we rewrote that function of x as a function of u times this factor here, which is a conversion factor, times du. So that's what I mean when I said that we use a conversion factor here. What it allowed us to do then was take the x and map it over to a new variable u. Now we're going to look at what happens with double integrals, and we have a very similar situation that happens with double integrals. So let me rewrite this here so we can see the similarities. Again, if we use a substitution formula with f dx, we convert it over to a function of u times some conversion factor times du. And so we can expect a similar thing to happen with the double integral, and as a matter of fact, it does. If I look at the double integral of f of x, y, dA, and I want to do a change of variables or a substitution formula and convert this over to, for example, a function of u and v, I would rewrite my function of x and y as a function of u and v. Then I would multiply it by a conversion factor, and then of course the dA would become either du dv or dv du. So basically what we have happening here, instead of just mapping a single variable x over to a single variable u, we're going to take some region in, say, the xy plane, and we are going to do a linear map which converts it over to a area then in the UV plane. And that every single point in the XY plane will get mapped over to a point in the UV plane. And the conversion factor that we use to map this, so the conversion factor, sorry about that, factor that we are using here is called the Jacobian. And the Jacobian of U and V will be the determinant of the matrix, which has across the first row the partial of x with respect to U, partial of x with respect to V, and then across the second row the partial of y with respect to U, partial of y with respect to V. Now, if you're interested in exactly why this particular conversion factor works, you can check Khan Academy, who does a decent job, I think a pretty good job actually, of showing you what that conversion is about. It's kind of a difficult concept at this point, but it is basically, the Jacobian is what allows us then, or it maps functions of functions of x and y over to functions of U and V. So in this video, what I mainly want us to do is just look at how it is we can calculate the Jacobian. So let's look at a couple of examples here. Let's find the Jacobian for each of the following. We will start with our first example where we have x is equal to u plus v and y is equal to u times v. Well, the Jacobian then will be equal to, again, the determinant of the matrix, which has the partial of x with respect to u, partial of x with respect to v across the first row, partial of y, with respect to u, and the partial of y with respect to v across the second row. So this is going to be the determinant of the matrix. So we go back to our x equation. We'll find the partial of x with respect to u, which is 1, partial of x with respect to v, which is 1. Then we'll go to our y equation. The partial of y with respect to u is v. The partial of y with respect to v is u. And then to find the determinant, remember we multiply in this direction, so 1 times u is u, minus what happens when we multiply in the other direction, which is v. So the Jacobian for this particular conversion would simply be u minus v. Let's go ahead and try one more of these, and then we'll talk about in our next video how it is we can then use the idea of just Jacobian to actually do a change of variables for double integration. So one more of these to do before we go there. Let's let x equal to e to the u times the cosine of v. I'm sorry, not x, cosine of v. Sorry about that. And y equal to e to the u times the sine of v. Then the Jacobian is going to be equal to the determinant of the matrix, which has across the first row the partials of our x function. So we start by taking the partial of x with respect to u, which is just e to the u cosine of v. And then the partial with respect to v, which is a minus e to the u sine of v. Next, we'll use our y equation. We'll go across the next row. We'll take the partial of y with respect to u, and that's just going to give me back an e to the u times the sine of v. And then we'll take the partial of y with respect to v, which is going to be an e to the u times the cosine of v. And for the determinant of this matrix, remember, we're going to multiply in this direction and subtract what happens when we multiply in the other direction. So I'm going to get e to the u squared cosine squared of v minus a negative e to the u squared times a sine squared of v. And I can factor out an e to the u squared, which we'll talk about in a minute what that is, and that would leave me then with a cosine squared of v plus a sine squared of v, which of course we know goes to 1. And when we square in e to the u, we multiply those exponents, so we get e to the 2u. So the Jacobian of uv is just simply e to the 2u.